Hello and welcome to this Python tutorial. So in the previous tutorial we initialized our artificial neural network by defining it as a sequence of layers, and now in this new tutorial we are going to add the first layers of our ANN, which is the input layer and the first hidden layer. Alright, but before we do that, let's refresh our memories to remind us about the different steps of how an artificial neural network is built. So here's the slide. This is the slide from the intuition tutorial, and as we can see, an artificial neural network is built in 7 steps. The first step is to randomly initialize the weights of each of the nodes to small numbers close to 0. So that will be done thanks to the dense function, which we take from this dense module here that we imported previously. So basically, this dense function that we're going to use is going to take care of this first step. Then, next step, our first observation row goes into the neural network. And as we can see in this step 2, each feature is going to one input node. So we already know the number of nodes we'll have in our input layer, and this number is nothing else than the number of independent variables we have in our matrix of features. So what is this number? That is 11 independent variables. So that means that in our input layer, we'll have 11 input nodes. Then the third step is forward propagation. So from left to right, the neurons are activated by the activation function in such a way that the higher the value of the activation function is for the neuron, the more impact this neuron is going to have in the network. That means the more it will pass on the signal from the nodes on the left to the nodes on the right. And so speaking of activation function, what we'll have to do in this tutorial to define the first hidden layer is to choose an activation function. And as a reminder, there are several activation functions, and the best one, based on experiments and based on research, is the rectifier function, which you can see right here. We also have this sigmoid function, which is really good for our output layer, since using the sigmoid function for the output layer will allow us to get the probabilities of the different class. That means that we'll get the probability that the class equals 1 for each of the observation, and even the new observations of the test set when we'll make our predictions. So that means that for each observations of the test set, we'll get the probability that the customer leaves the bank and the probability that the customer stays in the bank. And so that's great because, as Kirill explained when he described the model, we are trying to build a segmentation model, and by getting the probability thanks to the sigmoid activation function for the output layer, well, we will be able to see which customers have the highest probabilities to leave the bank. So we will even be able to make a ranking of the customers ranked by their probability to leave the bank. So that can be very useful, and then you can segment your customers according to their probability to leave the bank and according to what you decide to do in terms of business constraints and business goals. Alright, so to summarize, we'll choose the rectifier activation function for the hidden layers, and we'll choose the sigmoid activation function for the output layer. Alright, so then step 4. In step 4, the algorithm compares the predicted result to the actual result, and that generates an error. And then in the step 5, this error is back propagated in the neural network from right to left, and all the weights are updated according to how much they are responsible for this generated error. And by the way, there are several ways of updating these weights, and this way is defined by the learning rate parameter, which decides by how much the weights are updated. Alright, and then we have step 6, where we repeat steps 1 to 5, either after each observation or either after a batch of observations, like for example, we update the weights every 10 observations going into the network. And finally, step 7, when the whole training set passed through the ANN, that makes an epoch, and we repeat many more epochs. And we will see how many epochs we choose to do in the end. Alright, so that was a quick refresher of how we can train an artificial neural network using stochastic gradient descent. And so now let's do this step here to add the input layer and the first hidden layer. Alright, so the first thing we're going to do is take our classifier. That's the classifier we initialized in the previous step by creating an object of the sequential class. And now we're going to use a method of this object, which is the add method. And as you might have guessed, this add method is the method that we use to add the different layers in our neural network. So remember, an object is separated from the method by a dot. Here we go. And as you can see, the first method here on this list is add. So I just need to press enter. Here we go. And now let's add some parentheses and see what we need to add in this add method. So as you saw the yellow rectangle appear here, there is only one argument, and this argument is the layer that we want to add to our ANN. So as you can see in this title of this section, right now we're going to add two layers, the input layer and the first hidden layer. And we're going to do this thanks to the dense function which I've mentioned earlier. And so right now we're going to input dense and then some parentheses. And as you can see now, there are a lot of arguments. And so we'll add the different arguments of this dense function. And these arguments are going to be all the parameters that we can see on this slide. That is, how the weights are updated, what is the activation function we use, and what is the number of nodes we want to choose in the layer, and what is the number of input nodes. Well, everything happens here in this dense function. So let's have a better look at what we need to input by pressing here Command I to get into the help, and that gives us all the different parameters that we need to input. Alright, so let's have a look at the first parameter. The first parameter is output dim. Okay, so what is output dim? That is simply the number of nodes you want to add in this hidden layer. Because more precisely what this add function does is not to add the input layer in the first hidden layer. What it really does is add this hidden layer. And by adding this hidden layer, we're specifying the number of inputs in the previous layer, which is the input layer. So the output dim here is just the number of nodes of the layer we are adding in this add function. So that's the number of nodes of the hidden layer. And now the big question is, how many nodes are we going to add in this hidden layer? That's a big question in deep learning. You'll get a lot of questions like that in forums or deep learning discussions. And the answer that comes most of the time is that it's art. Indeed, there is no rule of thumbs on what would be the optimal number of nodes in this hidden layer. We can give some rules, like for example, if your data is linearly separable, well, you don't even need a hidden layer, and in fact, you don't even need a neural network, but we have better than that. I would not characterize it as a rule, but rather as a tip. And this tip is not based on theory, but rather based on experiment. This tip is to choose the number of nodes in the hidden layer as the average of the number of nodes in the input layer and the number of nodes in the output layer. That is the tip you want to use if you don't want to be an artist. And if you want to be an artist, well, what you have to do is experimenting with a technique called parameter tuning. Parameter tuning is about using some techniques like k-fold cross-validation, for example, which we'll study in part 10, model selection and ensemble model. And this k-fold cross-validation technique consists of creating a separate set in your data set besides the training set and the test set that is called a cross-validation set. And basically in this set, you experiment different parameters of your model. So typically the number of hidden layers and the number of nodes in the hidden layers. And then you test the performance of your different models with the different parameters. So we won't do it now, obviously, because we want to focus on our artificial neural network, but keep that in mind, and keep in mind that we will do this in part 10, and that it will help us choose the optimal parameters of our model. But for now, we're going to take this tip, which is to take the average of the number of nodes in the input layer and the number of nodes in the output layer. So that is, if I go back to Variable Explorer, well, the number of nodes in the input layer is 11, because the number of nodes in the input layer is the number of independent variables, so 11. And the number of nodes in the output layer is 1, because as you saw in Kirill's intuition tutorial, when the dependent variable has a binary outcome 1 or 0, well, there is only one node in the output layer, and so the average is 11 plus 1 divided by 2, that is 6 nodes in the hidden layer. So that's what we'll choose for the output dim parameter here, and therefore the first argument that we'll input here is output dim equals 6. Alright, now next argument. The next argument is init. So that corresponds to the step 1 of the stochastic gradient descent. And so what we have to do now is to randomly initialize the weights as small numbers close to 0. And so we can randomly initialize them with a uniform function. Here we see that we have the Glorot uniform. This is kind of a uniform function to initialize the weight. And we even have more simple. There is the simple uniform function, which will initialize the weights according to a uniform distribution. And besides, it will make sure that the weights are small numbers close to 0. All right, so let's input this second argument init. Here we go, init equals, in quotes, uniform. Great. Now comma to input the third argument, and the third argument is the activation argument, which is of course the activation function we want to choose in our hidden layer. So as I just explained, we're going to choose the rectifier activation function for the hidden layers and the sigmoid activation function for the output layer. So here, since we are in the hidden layer, we're going to input here activation equals, and actually the parameter that corresponds to this rectifier function is called ReLU, R-E-L-U. All right, so let's see if we have all the arguments here. We specified the number of nodes in the hidden layer, we specified the initialization method, and we specified the activation function. If I select this line right now and press Enter to execute, I get this raise exception error. And why is that? It's because there is another parameter that is kind of hidden here that we must input as well. Well, I think you might guess what it is. It is actually the input dim parameter. Even if it appears as one of the last arguments here, this is actually a compulsory argument. Because what is this argument? This argument is the number of nodes in the input layer. That is the number of independent variables. And why is it compulsory to add this argument at this stage? It's because so far our artificial neural network is simply initialized. We haven't created any layer yet, and that's why it doesn't know here which nodes this hidden layer here that we are creating is expecting as inputs. So that's why we have to specify this argument here, but then when we'll add some other hidden layers, well, since this first hidden layer will already be created, we won't need to specify this input dim argument for the next hidden layers. Because since the first one will already be created, the next hidden layer will know what to expect. Alright, so let's add this last compulsory argument here, which is the input underscore dim, and that is equal to 11, because we have 11 independent variables. Alright. So now we're ready to execute. It should work fine. So we'll select this line and execute. And as you can see, our first hidden layer and at the same time our input layer were very well added in our artificial neural network. So perfect. Now we're ready to move on to the next step, which is to add a new hidden layer, which to be honest is not necessarily useful for our data set, but we're going to add it anyway for two reasons. First of all, because this part is called deep learning, and deep learning is defined as an artificial neural network with many hidden layers. And the second reason is simply that if you need to add more hidden layers in your neural networks, well, you need to know how to do it. And that's what you'll learn how to do in the next tutorial. And until then,